check, check, check. Check, check, check.
So it's recording now.
Okay.
I can also cut the...
Yeah, so cut the first and the interval out.
Oh.
It's not too difficult, right?
No. It's just what you do is basically you cut the file, MTS file.
Okay. So hello everyone, let's get started. I've just heard that the Blackboard was available only to instructors and TAs, but not to students, which is not optimal, but I've heard that it got fixed. So you should be able to log in and see the course, and hopefully you can see the PDF document from the recitation yesterday. Good. Other announcement that homework 1 will be out tonight, and hopefully it will be lots of fun for you. And I also hope that you will see it on Blackboard. So your solution, there's a description what you should do with that, but you should submit on Blackboard. And we want to make anonym the very first. We didn't put description there, but the very first problem should be anonym, so you don't put your name on that one. Okay? Because we have some plans with that. That's secret yet. Okay? So the goal of today's lecture is to discuss some basic definitions and properties of convexity, convex functions, convex sets. But before that, let's just review Simplex method once more. So this is my one slide description of Simplex algorithm. So you remember, so this is the phase 2 of Simplex algorithm. So you have a canonical form that looks like this. So this is your cost function here. Right? It just says that z is z naught plus cm plus 1 xm plus 1 plus cn xm. Okay, and from this we know our goal is to minimize z. So we know if all these cm plus 1 cn constants, if they are all non-negative, then the optimal solution is if all the non-basic variables, that is xm plus 1 and so on xn, they are zeros. Right? So that's how we can minimize. If we do a pivot in ARS, so so if all these components, cm plus 1, cn, they are all non-negative, then we are done. If there is one that's negative, then we can do pivot in that column, and it will mean that that variable xs will come into our basis, and some variable among x1, x2, xm will go out. Right? So if we do a pivot, say, in ARS, then you can check that the new cost z tilde will satisfy this equation, and the new variable on the right hand side b, the j coordinate of b, will satisfy this equation. When we do a pivot, then we want that all the variables x1 and so on xn, they should be non-negative. The non-basics are already 0, so we have constraints only on these variables now, x1 and so on xm. And you can check if in this equation, so if the non-basics are all 0 except xs that we are going to bring into the basis, then of course say x1 is b1 minus a1s xs. Right? So x1, you can just read this equation. You know that here everyone is 0 except xs that we want to bring into the basis. In other ways, we increase the value of xs from 0 to some positive number. So we have this constraint for x1 and so on, and we have this constraint for xm. We want all these variables to be non-negative, and we want to decrease the value of z as much as possible. So what will be the solution for that? The solution will be that we choose xs to the minimum of all these values bi over ais. Right? If xs is larger than this quantity here, then one of these constraints wouldn't be satisfied. Okay, and let r be the argmin of these quantities, and it means that we will bring xr into the xr will go out to the non-basic variables. And you can also check if you do this pivoting method, then the new b value, b tilde, it will be non-negative again. So you can repeat this whole process till you stop. Okay, so if you missed the first 2 lectures, but just remember this, then it will be enough to reconstruct the previous lectures. Any question about this so far? No? Good. So the only drawback here is that we need a canonical form to start this simplex algorithm. And generally, we don't have that. We just have a standard form. And the question is, how can we find a feasible solution of the standard form that's in canonical form? But that's very easy. You just need to introduce new variables. So for example, if you want to solve this problem here, we have this is our cost function. We want to minimize z. We have 2 constraints. And we just introduce 2 extra variables, x, x6 and x7, so one extra variable for each equation. We forget our original cost function, and this will be our new cost function, the sum of these slack variables. They are non-negative, so it means that if we can find a solution where x6 and x7 is 0, then we have a feasible solution to the original problem. Right? Because all the variables are non-negative and they satisfy these constraints here. And now this has a special form, and it's very easy to rewrite this in a canonical form. Okay, so you can see that here. So that's what I did. I just rewrote this system in a so-called tableau form. So you can see that our goal is to minimize W, which is where minus W plus x6 plus x7 is 0. And here you can see that this is just the description of the first constraint, and this is the second constraint. So 4 times x1 plus 2 times x2 plus 13 times x3, and so on. That's 17. So we have this system. We want to transform it to be in canonical form. But that's very easy, because we just need to remove. So what do we need to do? This is already a basic variable. We need to remove this one from here and this one from here. We want to have zeros here, and then we will have a canonical form. So we just need to subtract the second equation from the first one and the third equation from the first one, then we will get zeros here. So that's what happened here. And now this is in a canonical form, so we can run that simplex algorithm that we just discussed to minimize the cost function of W. If that cost function will become 0, then we found a feasible solution. And from that feasible solution, with the original cost function, we can run again the second phase of simplex algorithm, and that will solve our original problem. Clear? Very good. So on the slides, you can check these steps. So this is our tableau form. We check the cost functions. This is negative. So we decide to make a pivot here, and we check the ratios. That is 17 over 13. That's smaller than 7 over 5. So we do a pivot here. You will get, after this pivot, you will get a new system. Again, you check. Now this will be your cost. You see a negative value here. So you choose this column. X5 will come to our basis. And again, after checking these ratios, then you decide to do a pivot here. And after that, you cannot see any negative numbers here. So we are done. And you can just read the solution from this tableau, and you will see that x6 and x7 is indeed 0. So we found a feasible solution to the original system. Now, when we have this feasible solution, we just replace this cost function with the original cost function that we wanted to minimize. So we replace this cost function with our original cost function and continue the second phase of the simplex algorithm. Some tiny problem, though, is that now this is not in canonical form. But again, this is very easy to transform this to canonical form. Again, you just need to set this to. So what you do is that you multiply this by -4 and add to this equation, and this with -10 and add to this equation. And that's it. And then you can run the second phase of the simplex algorithm. One thing, though, is that you shouldn't do pivot on x6 and x7 anymore, because they were artificial variables. You don't want to bring them to your basic variables. You run the second phase, and when you stop, you found your optimal solution of the original problem. OK, so this looks a bit complicated. with MATLAB, it's just a few lines. So for example, if you want to minimize, so this is the coefficients of your cost functions. This is your matrix A, matrix B. You can set up constraints on the bounds. That is, all the variables, they are lower bounded by zeros. And then after that, just 2 lines to run the simplex algorithm. If you don't want to run the simplex algorithm, but you are happy with some other algorithm for solving linear programs, then you don't even need to use this line. OK? Any question about linear programming? There are lots of other algorithms to solve this. So for example, there's one famous, it's called crisscross algorithm, which looks like simplex algorithm, but you don't even need to have these 2 phases. It doesn't need to start from a canonical form. You can just give the standard form to the algorithm and it solves it. But this is the most famous. That's why we discussed this one. OK, a few relevant books. If you are interested in this, then I recommend reading these ones. So as a summary, we discussed the standard form, canonical form of linear programs. We defined basic solutions, feasible solutions, optimal solutions, degenerate solutions. Degenerate was when any coordinate of B, component of B, could be 0. We saw that the simplex algorithm has 2 phases. And we discussed one application, how to do classification with linear programming. OK, if you have more questions, just come to my office hour after this lecture, and we can discuss them. And now we continue with convexity. Probably we won't be able to finish everything today, so I might need some 10 more minutes the next lecture to discuss everything about convexity. So the goal is just to define convex sets, convex functions, and discuss some of their basic properties. I really hope that many of these properties are known to you. So I just hope that at least the basic definitions are clear, but let's review them. If you want to read more about convexity, convex sets, I recommend these 2 books. And I brought them here. This one is available online, too, so you can just download it. I believe this is not available online, but it's a very good book, too. So just I give it to you. And if you got tired, you can read it during the lecture. OK, so we will need a few basic definitions, such as line. So we have points x1 and x2, and we say that the line is that set in an n-dimensional Euclidean space, which is defined with this equation here, where theta is a real number. And this line goes through x1 and x2. Line segment, on the other hand, is the same as line, except theta is in the closed interval 0 and 1, then it's a closed line. If it's in the open interval of 0 and 1, that's an open line. OK, so we say that set C is affine if for any x1 and x2 in set C, the lines through x1 and x2 is also in C. So another way that for all theta this is in C as well. We can define the affine hole as the affine hole of C is just the linear combination of these points, theta 1, x1, and so on, theta k, xk, where all these xi points are in set C, and we have this constraint that the sum of these thetas they are 1. Okay, and the affine whole is the smallest affine set that contains C. That's a theorem. So why it's that important to define them? Because you can prove that solution set of linear equations, they are affine set. So let's set C be those points x, those x points, where A times x is B, where A is a matrix, B is a vector. And now we can prove that that set C is an affine set. So that is, if A times x1 is B, A times x2 is B, theta is a real number, then what we need to prove that A times the affine combination this is B, right? Okay. Few more definitions that we will need. We need to discuss some definitions from topology, such as what we mean on boundary of set C. Who hasn't heard about this definition, that boundary? Who knows what boundary is? What's the difference? So once again, okay, I ask again. So who hasn't heard about the definition of boundary? Okay, there are a few ones now. So we have a set C, and we say that X is on the boundary of C, and we denote this by this delta C, the boundary set of C, if for a small enough epsilon, we can, and we define a ball around X. That's denoted by this Bx epsilon. So if we can find an epsilon such that the ball, the intersection of the set C and the ball is not empty, and the intersection of the ball and the complementer of C, that's not empty either. Is it clear to those ones who have never heard about the definition of boundary? Good. So we say that X is an interior point of C if you can find an epsilon such that a small enough ball will be entirely, around X will be entirely in C. And now there comes a tricky definition, which is the definition of relative interior that we denote by rel int. C. Yes?
The boundary should be for all epsilon, right?
For small enough epsilons, right? So you can find.
I thought it had to be for every epsilon.
Yeah. So epsilon. So you can find a epsilon naught, such that for all epsilon that's smaller than epsilon naught. All small enough. So in the interior. So which definition?
Boundary.
Boundary.
I thought it had to be true for all epsilon.
Yes. Yeah.
Yeah. Epsilon
Yeah.
zero.
But that's enough just to have a small enough term. Right? Yes. Okay, but here for interior point, right, it's clear that I just want those ones that are small enough. Yes?
Sorry, can I just double check once more? Because I think we have the same definition. I think it's still not clear. I think the definition of boundary is for any epsilon ball we choose, there exists at least one point in the interior and at least one point in the exterior, right?
Yes.
Right. Well, the definition of interior is that there exists an
This-
epsilon
That's
such that.
so not just one. It should be small enough, right? So it's so I'm just saying that there's an epsilon naught. That if epsilon is smaller than epsilon naught, then the whole ball is inside. I just defined like this.
True.
Okay.
Yeah, right. I just think the boundary definition, like the way it's phrased right now, is not very.
But it's right this way true, this way as well, right? But is it wrong?
I think according to this definition, if you put a point which belongs to the interior of the sea, it can still be on the boundary because you can find a relatively larger epsilon and you cover it inside of your house.
No. So if I define like this, it cannot be in the boundary, right? Because I'm saying that for small enough epsilon. So if
So you mean by small enough, it's like
For-
is this
for-
epsilon and for all the relative
For
number
all small-
smaller than epsilon,
yes.
it should be all like that.
yeah.
Yeah, that makes sense.
Okay. So this definition, I think it doesn't matter which one we use. Good. Questions? Okay, so the relative interior of C is so we say that X is in the relative interior point of C. If X is in C and for some epsilon again small enough, the ball around X with epsilon radius and the intersection of the affine hole of C, that's in C. So in other words, we just do the same definition that we had for interior, but we restrict this ball to be in the affine set of C. So what's the difference here is that, for example, if I have this line here, and I want to talk about this point, whether this is interior or not, if the whole space is a, say, two-dimensional space, then this point wouldn't be the interior point, because if I have a small enough ball around this point, right, that wouldn't be entirely in this set, the line. But if I restrict the ball to the affine set of this space, then I can say that this is indeed the interior point.
What's the difference between, like, in conceptually, interior and relative?
So the conceptual is just when I'm talking about this object, the question is whether you consider this as, say, one-dimensional object or two-dimensional object. And if I consider this as one-dimensional object, then this will be an interior point because that's the ball. The ball is an interval. But if it's a two-dimensional object, then this would be a ball. And that would make this point not interior point. It would be a boundary point. Yes?
Don't we also have, don't we also have to demand that the ball intersection with the affine hull of C is not empty?
Yeah, so it's,
Did I miss that?
yeah, it shouldn't be empty. You're right.
Right. Because otherwise you can have
Yeah, the empty set,
and
yeah.
you can have an empty ball like over there. And
Mhm.
yeah.
So if say, yeah, X is already in the, yeah, it always contains X, that's true. Because epsilon is positive number, right? So you choose a point X in C.
And C, okay.
Yeah, good point.
X and C. Yeah.
Okay. So we define the closure of C, that is CLC, as C union with the boundary points. And we can also define the relative boundary as the closure of C minus the relative interior of C. We say that C is closed if it contains all its boundary points. C is open if the intersection of the boundary points and C, that's an empty set. And you can define sets that are not open, not closed either. Is it clear? And we will say that the set C is compact if it's closed and bounded. We are in n-dimensional spaces now. Generally, in topology, it's defined more generally, but for us, that will be our definition. Okay, so after this, we can define convex sets. We say that a set C in a d-dimensional space is convex if and only for all x1, x2 in set C and for all theta in the between 0 and 1 closed interval, the linear combination, or I will say this is convex combination of x1 and x2 that's in C. So in other words, the line segment between x1 and x2 that's entirely in C. We will say set is not convex if this is not true. You can find x1 and x2 such that the whole line between x1 and x2 that's not in C. We will say that a set C is strictly convex if the open line segment between x1 and x, so between x1 and x2 is in the interior of set C. So I choose x1 and x2 from set C, and the open line segment should be in set C as well. So for example, this triangle here, it's convex but not strictly convex, because if this is x1, this is x2, then this line segment is not interior of set C. Clear? Okay, so here are a few examples of convex sets, such as empty set. It's by definition, it's convex. The singleton set, so it's just one point, that's convex. The whole space, so it's a d-dimensional space, that's convex. As we defined, lines are convex. Line segments are convex. Hyperplanes are defined as those x vectors in an n-dimensional space with which A transpose x is B for some A n-dimensional vector and B real number. They are convex, and half spaces, they are convex as well. So half spaces are defined with this equation. Those points, those x points in the n-dimensional space where A transpose x is not bigger than B. Any question about these definitions? Good? Yes?
Strictly convexity is on X plane or
which are strictly convex.
Like you talked about strictly convex, right?
Yes. So basically what you need to check is that if you can find a line segment that's not in the interior point of the set.
Right, so lines and like the next example, they are not strictly convex.
The lines, they are not.
Okay. And hyperplane is strictly convex. That's
Hyper-
what the question was.
Hyperplane, so it's
It
not.
doesn't have the boundaries.
So if it's a, so you have a closed, so this one, right?
Yeah.
Yeah, so the question is, it's not homework question, right? So I don't know to answer or not. So if x1, so how a hyperplane looks like? Yes?
Because you mentioned on plane in 3 dimensions, if you assume that the whole plane is going to be boundary, right?
Yes.
So we're
So-
always on the boundary, so it's not strictly.
yes.
That's
But some of these basic questions will be in homework, right? That we need to prove that some of these sets are convex, I think. So I have to be careful what to answer here. Okay, other important convex sets are Euclidean balls. So we define the Euclidean ball with radius r with this equation that are those x points in the n-dimensional Euclidean space. So with balls, we have a center point x0 and the radius r, and the constraint is that the distance between x and x naught, that is the norm of x minus x naught, should be not more than r. How about LP balls? Who hasn't heard about LP balls yet? Okay, so there are a few people. So we define the LP norm of a vector with this equation. So you add the, so it's the sum of xi absolute value to the power p. You add these numbers, and then you put this to the power of 1 over p. It's the generalization of the 2 norm, right? And you can prove if p is not smaller than 1, then these balls will be convex sets. So I tried to draw a picture. So this would be the L2 ball. The L1 ball has straight line boundaries, and the L infinity ball defined as the limit when p is going to infinity, and that would be the supremum norm, and it would look like this square here. So they are all convex sets. However, if p is between 0 and 1, then, oops, you can show that the LP balls will look like this star-shaped areas, and that's not convex. Okay. We will need the definition of the polyhedron as well, but I will do that after 5 minutes break. Polyhedron definition, they are the solution set of finite number of linear equations and inequalities. So in other ways, polyhedron P is that set of x's where for some parameters a, b, c, and d, this holds, right? So A transpose X is less than B, and C transpose X equals D. If you want, we can have a matrix notation too, with matrix A and C and vector B and D. And we will just say that polyhedron is that set of points where this inequality and this equation holds. And polytope, we will say that a polytope is a bounded polyhedron. In some books, this is not the definition. You might find some books where polyhedron will be bounded polytope. So they just mix these two things. Okay, and you can think of a polytope as an intersection of half spaces and hyperplanes, right? So this polytope here is a intersection of those half spaces that are defined by these normal vectors a1, a2, a3, a4, a5. Is it clear? Okay, we say that we will need the definition of convex hole, and it will denote it by, so C is a set, for example, these points, and the convex hole of these points is a convex combination of finite many points inside of set C. So theta 1, theta k, they are non-negative numbers such that their sum is 1. And x1 and x2, xk, they are points in set C. Okay, and you can see that the convex hole of these finite many points will look like this polytope here, and the convex hole of this set would be this bigger set here. Definition is clear, right? And there are some basic properties such that the convex hole of C is the smallest convex set that contains C. And of course, the convex hole of C is convex. The set C is inside of the convex hole of C. And you can also prove that for any two sets, C and C prime, that are convex, if C is inside of C prime, then the convex hole of C will be inside of C prime as well. Okay? We will need a definition of simplex as well, and simplex is a convex hole of some finite vectors, say v naught, v1, v2, and so on, vk. In other words, so this is a convex combination. Oops. Okay, so this is a convex combination. And we have another constraint that these sets, so it's k plus 1 vector, right? It should be so-called affine, they should be affine linearly independent set, on which we mean that v1 minus v0 and vk minus v0, these k vectors, they are linearly independent. Okay? Yes?
Can we go back one slide?
Yes.
I think it should be inside convex of C1.
C prime is a convex set.
Oh, convex set.
So the convex whole of C is itself. Other questions? Okay, definition of simplex is clear too, right? So how do they look like? So for example, a one-dimensional simplex would be the convex whole between these two vectors. A two-dimensional simplex would be the convex whole of these 3 points. And the three-dimensional simplex, you have 4 points in the three-dimensional Euclidean space, and it's just the convex whole of that 4 points. Okay, so the important thing is that 4 points, they should be in general position. They cannot be in a hyperplane. Okay, we can generalize the convex combination from finite many sums to countably infinite many sums as well. So that was the original. So the original definition was for 2 points, right? And you can prove that that's equivalent to the convex combination of finite many points. And you can generalize this even further, that you can prove this, that set C is convex, then if you have infinite many points in C and infinite many theta non-negative numbers, such that their sum is 1, then this combination, convex combination, will be in C as well. And you can generalize this even further to uncountably many sums, and what would be that? That would be integrals, right? So you can prove this one as well, that if P is a density function, C is a convex set, then the mean of a random variable that has density P, that will be in the set C. Well, you need to assume that this integral exists. So in other ways, if you have a convex set, you define a distribution on that convex set, then the mean of that distribution, if it exists, that will be in the set itself. Is it clear? Who got lost? Who didn't get lost?
I have a question.
Yeah.
Like, should this function define only on C though? Like, you're defining on the entire real set, like Rn space.
Good point. Yeah, it should be defined on the set C.
Okay.
Otherwise, the mean could be
It's
out.
not normalized.
Yeah. So the support of P, it should be
Yeah, okay.
in C. Good point. Yeah. So it's not even true, right? What I just wrote here. So if you understood what was not good, that's not good. Good? Right, so if I just write this here, then P and C, there's no relation between them. So the support of P is inside of C. Okay, we will need the definition of cones. And we will say that C is cone if for any point x in C, and if for any point, if I multiply this point with a non-negative number, that vector will be inside of C as well. Okay, so for example here, I choose this vector. If I multiply this with any non-negative number, that so-called ray should be inside of set C as well. This might be not convex. Can you imagine a non-convex cone? Yeah. Right? Or I could talk about this set too, right here. That's non-convex either. But there are convex holes as well, convex cones as well. Convex cone is a cone that's convex. That's the definition. And we can define we can also define conic holes as well. And the definition is straightforward, right? So it's the conic hole of set C is linear combination of points inside of C such that these coefficients, they are non-negative. So differences in affine, when we had affine combination, then we needed that this sum is 1. When we had convex combination, then we needed that the sum is 1 and they are non-negative. When we have conic combination, all we want is that these coefficients, they are non-negative.
Sorry, what's the example for non-convex?
So the complementer of the convex form, with this one. Okay, an example of convex cone will be the positive semi-definite matrices. So who doesn't know what it means positive semi-definite? Okay, so there are a few people who knows it. More people. So the definition is, we say that a matrix A that size is n by n, it's positive semi-definite if and only if this matrix is symmetric and for any x vector in the n-dimensional space, x transpose AX is non-negative. So you might have seen some other definitions as well. So some people say that a positive semi-definite matrix doesn't need to be symmetric, but I don't like that. So it's a different religion. Let's forget those people. So we will just say that a matrix has to be symmetric and has to have this property as well, then it's positive semi-definite. Okay? And there's an important theorem which says that a symmetric matrix A is positive definite. Okay, so this is positive semi-definite. Positive definite if this x transpose AX is positive for all non-zero x's. We say that a symmetric matrix A is positive definite if and only if all of its eigenvalues are positive. And you can similarly prove that the symmetric matrix A is positive semi-definite if all of its eigenvalues are non-negative. Using this definition, we can define a partial ordering of square matrices. So we can say that M is not smaller than n if m minus n is positive semi-definite. And here is a theorem. We can define the set of n times n symmetric positive semi-definite matrices. That will be denoted, this set will be denoted by this Sn plus. And the theorem says that this set defines a convex cone. What do we need to prove? We need to prove that this set is a cone and this set is convex. How can we prove it's cone? We need to prove that if you have a matrix, you multiply this with a non-negative number, that if the original matrix was positive semi-definite, then the new matrix will be positive semi-definite. And we need to prove that it's convex as well, right? And that's pretty simple. So if A and B, they are n times n positive semi-definite matrices, then we need to prove that their convex combination will be positive semi-definite as well. So X transposed theta times A plus 1 minus theta times B times X. We need to prove that this is non-negative. And what's this? This is theta times X transpose AX plus 1 minus theta X transposed BX. This is non-negative because A is positive semi-definite. This is non-negative because B is positive semi-definite. So the whole thing is non-negative. We are done. Good? We will need to discuss how to represent convex sets, and we will discuss two representations, the so-called primal and the dual representation. The primal representation, it's itself with the convex whole. So the theorem is, we have the following theorem. So let S be a set in the n-dimensional Euclidean space. And then the theorem says that the closure of the convex whole of set C is the convex whole of possibly infinite many points in S. Okay. So you have a set S, arbitrary set. It doesn't need to be closed. Then you take its convex whole, and then you close it. Then this set, you can get this set as a convex whole of some of the points inside of S. But it might happen that we need to use infinite many points for that representation. And there's a dual representation. Which says that closed convex sets can be represented with half spaces as well in the following way. So the theorem again says that let S be a set in the n-dimensional Euclidean space. And then again, we defined the closure of the convex, its convex hole. And now we can prove that this set C is the intersection of all those closed half spaces that contain S. Okay, so we have this convex set here, and this convex set C is just the intersection of all these half spaces that contain the set. Yeah.
Does the boundary of the convex hole have to be linear or any kind of boundary?
The boundary of
the convex hole.
So as you can see, it can have curve, right? So even if there's curve, that it will be this set here, this convex set, it will be still the intersection of these infinite many half spaces. So if there's this curvature here, you just need infinite many half spaces to represent this set as the intersection of those infinite many half spaces. Okay. So there are a few important convexity preserving set operations, such as if we have a convex set C, then if I translate this set with a vector B, that will be convex. If I rescale the set, it will be alpha times C, that's convex. If I have two convex sets, C and D, then the intersection of C and D, that will be convex as well. And you can generalize this to arbitrary many intersection of convex sets. So say if I have say S alpha is a convex set where alpha is an arbitrary index set, it can be infinite many, uncountably many sets, then the intersection of all these convex sets, that will be convex as well. Yep.
So why was, if you go to the previous slide,
Mm-hmm.
one more. Why is closure necessary?
It's just yeah, we don't need it. It's some book defined the convex combination without closing it, so without using the endpoints. But how we defined it will define a convex closed set.
Okay. So it depends on the definition of convex.
Yeah, it's just yeah. So actually, yeah, the point is, okay, why we need it. So the convex set itself, it can be open. Okay. But the convex hole itself, that will be closed. So that's why we close it.
Okay. Oh, yeah, okay.
Okay. So
Yeah, that makes sense.
on the other hand, I already. So it depends a bit how we define the convex hole, whether the convex hole defines you a closed set or not.
Okay.
Okay?
Yeah, all right, it's just technicality.
Yeah. Right, so all that matters is that a convex set itself that could be open, and I need to close it. That's all. But this convex hull, how we define that, so already closing it.
Sorry, can we define a convex hull which is not closed? Like the definition of convex hull?
So
Not contain the boundary, basically.
yes, right. But so here, for example, if we have this triangle here, let me. And this is an open triangle. Okay, then it would be still open, right? Because any point, so, oops. Can you see this? So I define a triangle without its boundary.
Convex hull of that is still open, huh?
Yes.
Yeah, right.
But for this theorem, I need to close this whole set. That's all, but it's just some technical. Yeah, I'm still thinking that we might be able to avoid that, right? To closing it, but yeah, just for safety, let's use it for now. I will think about it. So in this one, it's clear why we did that, right? That we wanted to calculate the intersection with closed half spaces, and that will be closed. Okay, other convexity preserving set operations are the affine function. So if the affine function is defined by this, that A is a matrix, B is a vector, and the affine function is A times X plus B. And if C is a convex set, then its image, affine image, will be convex set as well. So the set sum, if C and C2, they are two convex set, then C1 plus C2, that will be convex set as well. So what do I mean on the set sum? That this is a set of vectors that are in the form of C1 and C1 plus C2, where C1 is all possible vectors from C1. So it's this one runs over all possible vectors in set C1, and this runs over all possible vectors in C2. Okay. And the direct sum, which is if C1 is an n-dimensional convex set, C2 is an m-dimensional convex set, then the direct sum will be an n plus m-dimensional set, and where C1 is, again, all possible vector from capital C1, C2 is all possible vector from capital C2 convex set. So this is the direct sum, that's convex set as well. Okay. Questions? Question?
Set sum only makes sense in the context when C1 and C2 are of the same dimension.
Which set sum, in set sum they are in the same, yeah, they are, yes. But the direct sum they can be in the same. Other questions? So there's an interesting one. It's called the pinhole camera function, or perspective projection function. So it says if let C be a subset of this space, which is a direct sum of an n-dimensional Euclidean space and the positive numbers. Let it be let C be a convex set, and we define the perspective projection with this function. So x1, x2, xn, it's an n-dimensional vector. T is a positive number. And so if I define this n-dimensional vector with z, then the projected image of this vector zt is just z over t n-dimensional vector. And if C is a convex set, then you can prove that the image of this set, that will be convex set as well. So I try to make a picture. But it's just disappeared. Here we go. So say we are in the three-dimensional space, and we have a convex set with coordinate x1, x2, and x3. And we have that's why it's called pinhole camera. So imagine that there's a hole in the origin, and you look what will be the shadow of this three-dimensional object in a plane that I put here where x3 is -1. And you can see that the coordinate of the three coordinates of a point with coordinates x1, x2, and x3 will be minus x1 over x3, minus x2 over x3, and minus x3 over x3. Right? So that will be the new coordinate. And we just forget this one and multiply this with -1, and that's what we mean on projective mapping. So if you have a convex object here and you take the image using this pinhole camera, then the shadow of this object, that will be convex as well. And you might wonder why it's useful at all, and we will discuss that next time. So I just need 10 more minutes to finish this, and then Ryan will continue with gradient descent. Okay, so thanks for your attention. If you have questions, then please come to my office hours, and we can discuss those questions there.